So today we're talking about the hydraulic strings. There are two types. One is the SO32 gauge group, young males. One is E8 cross E8. We call it in the lecture note for simplicity. I call it HO and HE. Roughly speaking, so hydraulic string is a left mover, anti-homomorphic. Anti-homomorphic are bosonic string, and then right mover which is homomorphic sector are superstring. Yeah. Then so there's a bit string theory, and this hybrid of these two different kinds of string is called heterosis. Okay. So the hydraulic string comes from the name heterosis. So here, as I mentioned, this is only well-defined d equal 10 and d equal to 26 for bosonic string. And so therefore the difference is indeed 26 minus 10 is 60 dimensional, and the extra 16 dimensional is compact fine on torus. On T16. And we think this size of torus is very small. At the end of the day, effectively this will give you d equal to 10 string theory. That's a rough idea of the bosonic string. So let's look at step by step. So we already knew that for S1 compactification, and also for homework, you get the Kalta-Klein momentum, and also winding number. And then, so we generalize to essentially TD, which is D copy of S1, direct product, D copy, and then we will just identify, so xi is the coordinate of the internal space is xi plus 2 pi and then I call, so shorthand notation, I call this is 2 pi wi, where ni is a winding number, corresponding winding number. So you have whatever. So let's look at the universal carbon of torus. Okay. And the winding number is essentially given by strings winding number is this one. For instance, winding number here, where this direction is E1, and this is E2. Okay. And then in that case, let me think. Oh, sorry. I think I should use E1 and E2. Yeah, E2 in the lower script, and then in this case, what did we say? N1 is equal to 3, and 2 is equal to 2. Okay. That's winding number for torus. So the torus is giving fundamental torus is here, N1 and 2 are giving. So W is equal to, by definition, this is equal to this. And the EI is the vector in RD that span lattice. I call it lambda D, maybe. Okay. First sum up. So this lattice can be tilted so that you can just introduce a metric on the lattice. On lattice lambda, such that the Gij is just inner product, standard inner product with respect to the Euclidean signature. In other words, Ei, Ej, I. Sum of I is assumed. Like this. And of course here, TD is, the torus is RD divided by 2 pi lambda D. I didn't use D here, so let's direction out. So lambda. Okay, so we again we try to introduce the so in the S1 complication we have the classical line moment and the winding number, and this capital W is the higher dimensional version of winding number. So we need also higher dimensional version of the classical line moment, which is a dual lattice. So the KK momenta for torus, it's torus complication. Takes a value on dual lattice. So dual lattice is indeed whatever. I mean, dual lattice. Let's go the vector for star I. That's a dual lattice for EI. So they span by and then so it satisfies the standard I dot E star J is delta IJ. That's the dual lattice. So, and then dual lattice is again, I mean, this the dual vector span lambda star, dual lattice. Lattice lambda star. And then, KK momenta takes a value. So, which, in other words, let's go MI. MI can take the sum of E star I dot MI. I call it MI. I mean, did I call PI or MI? Yeah, I think a bit weird notation. I should change this is WI in the lecture note. I think I will change. I think I should call WI in election node, and I should call this is Ni. That's more natural. That's more natural. And then it's a bit strange notation, but you have I after I. Okay. So this is the KK momenta. So I mean here I just draw the universal covering by just orthogonally, but you can take again. If you take E1, E2, then I think E1 should be something. E1 should be something like this one. Oh, sorry. No, definitely no. Sorry. E1 should be something like this. Sorry. Why am I writing such a stupid way? Sorry, I think I should write down more appropriate ways. I just got, yeah, it's okay. Maybe it's okay. Depends on how you draw. Okay. E star 1. So the E1 and E2 are also now, but if you take inner product of, E star 1 and E2 are also now, but E star 1 and E1, if you take an inner product, there's no trivial element, which is normalized 1. That's what it means. And also E2 is something like this one. Maybe something like this one. E star 2 is something like this one. So E star 2 and E1 are also now, but there is no trivial inner product between E2 and E star 2, and then the inner product should be normalized to 1. So dual lattice is more like a, so lambda is generated by these two vectors. It's hard to draw, but anyway, so you understand my idea. So this is lambda, whereas the lambda star is something like this will give you lambda star. So with a bit different lattice you will obtain. So the winding and the Kazakhstan momenta takes a value on the dual lattice. Then we can do the model expansion as usual for internal coordinate. The center of mass I alpha prime over 2 PR I log C and the oscillator. And this is 0 mode and the oscillator. And then you have untitled moment sector. So I'm not going to write down. Okay. So, and then if you look at 0 mode, 0 mode is a momenta. Again, we will have a similar thing. So P to L, I should take the following, the square root 2. I mean, it's as before, E star I, and then I plus. I will change the election node later, so I just change the notation. It's better to call W. Okay. Plus sign. So this is Kazakhstan momenta, and this is the winding number. For right moving sector, you have a different sign of combination. and then same piece. This is what we have seen. What we have seen in the S1 compactation. So namely, if you add them up, the conjugate of the momenta becomes T, conjugate of the winding number becomes sigma. Spatial direction, worldsheet spatial direction, worldsheet time direction. If you combine log z and log z bar, sorry, you know, as far as I remember, z is equal to something like a e to minus I, sigma plus I tau, it. And then if you use this, you plug that in, so the conjugate of the momenta should be T, T, and then the conjugate of sigma should be W. So that's just towards high-dimensional generalization is on complication. I hope what I said is correct. Let me check. I have a very poor memory, so let me check for T duality. Yeah, I'm correct. Yeah, it's okay. Okay. So then we can have the higher dimensional level matching condition and also mass of the string alpha m square, alpha prime m square is equal to 2 times n plus n bar minus 2 plus p dot p. Did I write a p dot p? Oh, I think I wrote fi. I think I should call it, this is the pi. Plus 1 over alpha prime. Okay. So this so this becomes the high dimensional analog of the mass. Remember that this for S1 case prime m square is equal to I already forgot, alpha 25 0 modes square plus n minus 1. For I think up to some normalization. Okay, up to some normalization. And this is also true for 2 alpha 0 bar square plus 4 and bar minus 1. Okay. And if you sum them up divided by 2, you get this. When you set d equal to 1. Okay. Do you understand? So if you just sum them up and divide it by 2, you get this. Okay. And the level matching. So this is mass spectrum, mass of string state at level n bar, okay, n bar, and then level matching condition is the n minus n bar is equal to pi dot wi, which is ni wi. And in fact, so this can be written. This can be written. This can be written Gij Wi, Wj, and this is Gij, Ni, and Nj. This Gij is a metric of dual lattice. So in other words, I define Gij here. After Gij is a dual lattice. So that metric of dual lattice. Okay, good. So, and one can consider the same thing for the T-duality. As you can easily imagine, in one case, it exchange an n between W. Okay, so n and W. So, which means that you just exchange the lattice for high-dimensional case. T-duality, you just exchange lambda and a lambda star. Okay, so, and then, if you do that, so if you change lambda and lambda star, indeed, so this one, so this takes a value of, again, lambda star, and then lambda, okay? So even if you change lambda and lambda star, nothing will change, but if you change lambda and lambda star, you have a negative sign here. So therefore, again, what we have, it's very similar to what we have seen in the S1 compactation, but the right moving sector or holomorphic sector, you get a minus sign. Minus sign. It's very similar to what we have seen in the S1 compactation. Okay. So now we can do a bit further simplification as follows. So we combine, so the T-duality is this one. So then we just combine, so the further simplification combine the big P, which is PL of PR, PR, which is the D plus D. So this D dimension lattice. The vector side. If you combine the PL and the PR, and simultaneously again, we just consider the linear combination of the lambda and lambda star. We just combine lambda and lambda star simultaneously. So therefore, what we are going to write is P takes a value of E star I and I plus EJ and WI. WJ. Okay. Where the capital E J is just a combination of j and minus ej, and the capital E star alpha I is equal to square root of the prime E star I and E star I. Okay, so this is the combination we will consider. And namely, so we just take the how to say? I mean two whatever column vector or even row vector, whichever is okay. Just combine two vector and then but the opposite lattice is with up to sign, plus or minus come from here. That's the I just combine them. Then the big P, which is combination of PL and PR, is just can be written in terms of using capital. It's just a rewriting. Then, if you do this rewriting, what you will obtain so this lattice satisfies the following property. Looks like silly things to do, but it's very important. I mean, once you go to higher dimension, the higher dimension, often human beings' intuition will fail. So you have to formulate it properly in mathematics, otherwise you make a mistake. So this is the proper formulation of the torus multiplication by using lattice. I mean, otherwise you make mistake. You have to be careful to properly formulate mathematically. So this lattice we call lambda d. D is the this 2D dimensional lattice spanned by Ej and then E star I, which satisfy the following condition. If you use the metric Lorentzian, with signature plus 1 to the D and minus 1 to the D. So this is Lorentzian, so that you can easily see plus from here and minus from here. And also it's an integral, which means that if you have a this is very silly way in the lecture note. So, sorry, oh yeah, it's okay. So, integral, which means that the Lorentzian, so integral means if you have for B and W, which takes the gamma dV, then the inner product with respect to this metric, B dot W, is integer. That's from construction from a lattice and dual lattice I have written here. It's obvious. And then it's even, which means that the if you have a B inside of this lattice, then B square is even integer. And maybe it's not positive. Yeah, it's not positive. Yeah, because of it's a Lorentzian metric. It's an even. And then furthermore, so let's see. Can you see the? Yeah, it should be easy to see. How can I see that? Let me think how to see that. So I understand what's going on. So, okay. So if you take the inner product of PR and dual PR, so essentially B squared, B can be written BL, and then it's like this way, BL and BR. Okay? And the B squared is indeed BLI BLI plus BRI times BRI. So that's inner product. And if you look at the BL, is just specified N and W. And if you take inner product square, essentially, and if you take inner product square, N and you just specify N and W. Okay? N and W, and you get the square. And the minus sign, so in the cross term cancel each other. And then only this square and this square and this square and this square, they add them together. Okay? Once you do that, therefore it becomes even. I mean, good. You're right. Quadratic term concept. Good. Thank you very much. You're right. Thank you very much. So if you look at the P square, you take the inner product with E star and E, and you just have a cross term. Okay, sorry, cross term. Okay, and then the cross term should come from you just multiply and it just take minus, and then that comes from Lorenz. Thank you very much. Then therefore it becomes even. Thank you. Yeah, thank you. And the self-deal. Self-deal, if the gamma d is equal to its dual lattice. I mean, by construction, it's true. I mean, you just combine lattice and dual lattice. So if you take the combination, that it becomes self-deal. Okay? And it's called unimodular, which is the if since we take the dual lattice again, so you have determinant G is essentially determinant of Gij times determinant of the inverse metric Gij. It should be 1. Okay. This is the metric from lambda, and metric for lambda star. So it should be 1. So that's a unimodular. Yeah. And then my lecture notes clearly write down the proper way to take an inner product. Yeah. So yeah, as I mentioned over there, and how corrected me p dot pw is capital P dot pw is pl, but I think it should be pl prime. There's a typo in the lecture note. This is equal to ni wi prime, and then prime, and then n prime I and wi. So that's inner product, which is the typo in the lecture note. Okay, and then this gamma dd is called Narayan lattice. Narayan is the Indian string theorist who is now ICTP. I think so. He has been ICTP Trieste, Italy, for a long time, I guess, as far as I know. Okay. And then partition function is bosonic string. So again, it's very easy. So you guys have to, you guys did a homework this one. The gamma dd is essentially 1 over tau 2 24 minus d over 2 eta tau 48, and times sum of q 1/2 pl square and q bar pr, pr and q bar 1/2 pr square. Okay. And of course, PL and PR takes PR and PL takes the value of the Narayan lattice. Yeah, so you already knew that. So this one coming from bosonic oscillator, and this one coming from zero mode of non-compact direction. So this is the integration. You already knew that. So this one coming from integration zero mode or alpha 0 or PL or zero mode in 24 minus d non-compact direction. And this is the counting bosonic mode, and this is another external internal momentum. You have to sum all this. So essentially, I just implicitly it's a sum of a Narayan lattice. For superstring, compact phi on this is bosonic, and this is the type 2 superstring of compact phi d-dimensional lattice. We have the same thing, tau 2, 8 minus d over 2, and 8 tau 24. Do you remember how do you get the 24? 1 over 4. Theta function, as you remember, this one comes from the so this one coming from fermionic mode, okay? RNS string, fermionic mode, the sum over all the boundary condition Ramon and V. Schwartz. And the Ada 24, how did it come? Do you remember? Why 24? Do you remember? So the superstring bosonic plus fermionic. Okay. And then you have left moving and right moving. And how many contributions of the right moving holomorphic bosonic model would give you Ada? How many exponents? Why over there it's 48? It's only bosonic. Why 48? You guys solved homework, right? Why it's this 48 appear here? Yeah, good. Thank you very much. So D is equal to 26. That's bosonic string. And the BC ghost will give you -2 contribution, okay? Or +2. I mean, the more precisely speaking, the bosonic string will give you -26 contribution and +2 contribution come from BC ghost. For holomorphic sector, you get a -24. This is holomorphic, and anti-holomorphic, you have another -24. That will give you 1/8 to the 48. Do the same thing for superstring. What is the bosonics contribution? For holomorphic sector. How many exponents? How many copy of Ada do you need? What is the dimension? D is 10. Okay? D is 10, and then bosonic string you get -10 contribution, and BC goes to give so 8. Okay? Holomorphic sector 8, -8. Okay? In anti-holomorphic sector you have a -8. You have a 16. Okay? You have a 16. Another additional 8 coming from each boundary condition will give you, holomorphic sector will give you whatever theta function divided by Ada. Theta function divided by Ada. Okay, let's go I to the 4th. Okay, for holomorphic sector. Holomorphic sector. For a fermion, we get the Ada to the 4th for holomorphic sector. Anti-holomorphic sector, you get the Ada bar to the 4th. At the end of the day, the 8 from holomorphic bosonic and the Ada to the 4th coming from fermionic bosonics, fermionic holomorphic state, and the 12, essentially -12 come from holomorphic plus bosonic fermion, and anti-holomorphic you get 24. Okay, and then of course this is equal to what? Zero, because of the Jacobi identity. Okay. And it's required to be 0 because of supersymmetry. Good. Okay, so let's move on. So So now, we consider bosonic superstring, both homomorphic and anti-homomorphic. Now we just consider homomorphic is bosonic. Or right moving. I consider the following situation. Now the partition function becomes like this way. So this is a hydraulic. Now lattice is no longer, you don't have any right moving to the compactified direction. Okay. So therefore the partition function can be written tau to the force eta of q bar eta q bar 24 Okay. So again, so left moving is left moving is bosonic. So the 8 to 24 come from really bosonic contribution for anti-homomorphic, and you have another additional contribution. Additional contribution here, and the 8 to 24 really come from the bosonic fermionic. So as I mentioned, 8 plus 4 is 12. So that's the contribution you obtain. And since we only have the 8, d equal to 10. So this is d equal to 10 and d equal to 26, but compact on torus 16. So therefore, non-compact direction is the non-compact direction d equal to 10. So therefore, if you integrate a zero mode, d is equal to now 16 here, 16. It's kind of bit. I shouldn't use d here in lecture note. Capital D here. Maybe I should use small d because it's different from dimension of the space-time. So this d is a dimension lattice indeed here. So d is 16, so you get the 16 minus 24 minus 16 is what? 8, and 8 divided by 2 is 4, right? And it's the same. 8 minus d divided by 2 is equal to 4. That is easy. How to do it? Okay. So the interesting part is again this Chorless compactation. Let's focus on this back. What kind of lattice it should take. So to see what kind of lattice it should take is that again we need to impose this has to be modular band. So in the superstring case, to derive this combination, we impose modular invariance. That is consistent GSO projection. So here to derive this one, we impose modular invariance. We do the same thing. We do the same thing here. And let's call this one is equal to, let's call P of tau. Let's call P of tau, and it's P tau plus 1 has to be equal to P tau, and then S of P minus 1 over tau is equal to tau to the 8 p tau. It should be. So this should be the case from the modular transformation of this theta. If you look at the theta and the eta, so the rest of the part is invariant on the T transformation, but under S transformation, they will get the tau to the minus 8. The rest of the part. That can be read off from the modular property of theta function and eta function. And then we just try to cancel with the rest of the part so that the anti-partition function invariant the modular transformation. So to read off, so we want this property. We want this property in such a way that you need to adjust lattice. Okay. So okay, we need to adjust the lattice in such a way that this p of tau satisfies this modular property. And then again, we use the Poisson summation formula for lattice. Which is given by here. I'm going to write them very, very schematic way. What we need is essentially this part. Lattice. So lecture note, you should put the x and the y, it has to be 0. In a lecture note. What we need is this part. And then okay, here what we want is alpha to the I to the tau. So the left-hand side is indeed equal to that one. Okay? Left-hand side and the lambda is equal to gamma 10. And then if you substitute this one, this will get tau to the 8. So since dimension of lambda is 16, you automatically get 8. Why do I get this? Oh, yeah, sorry. So alpha should be minus 1 I tau. Yeah. Minus 1 I tau. Sorry, I think it should be 1 over I tau. I mean, just this, okay, sorry. Lambda star should be, this part should be equal to P of tau. Okay. Sorry. So therefore, alpha should be, yeah, it's just this one. Yeah, it's okay. Yeah. Now, am I correct? Q bar is what is Q bar? Q bar is e to the 2 pi I tau bar. Oh my goodness, I totally got confused. Is it minus? I got confused. Is it true? Or tau bar? Tau bar and minus tau bar. Okay. Tau bar. And then why 1 over alpha So then one of our alpha should be this. There's 1/2 here and cancel and I tau bar. Sorry, I got confused in that case. I see. I understand. It's a bit confusing. I think I should call everything tau bar in that case. I mean, let's go tau bar here. This is definition. Let's call this is tau bar. But it satisfies this condition. So if you put tau bar, everything becomes bar. Okay, now understand. And you just substitute 1 over alpha is equal to I times tau bar, and this becomes P of tau and the volume of lambda, and this is P minus 1 over tau bar. This is the correct way to phrase it. Sorry. It's a bit confusing. So since this is an anti-homomorphic, but I wrote down everything in terms of anti-homomorphic language. But essentially, if you translate anti-homomorphic language, you should do that. Okay. So therefore, from here, what you conclude is that the lambda has to be equal to self-dual, which is lambda 16. Okay, so lambda 16 should be self-dual, and then volume of lambda 16 has to be 1. Okay. To get the P of minus 1 over tau bar, lambda also should take the value of lambda 16 to get the equality. And also, we assume lambda still is gamma 16, so it has to be self-dual. And to get the right modular property, the bottom has to be 1. That's a condition. Now for the partition function to be modular invariant, and then you just look at the mathematics book. So what kind of lattice satisfy this condition? 6-dimensional lattice, self-dual, and then the volume is equal to 1. It's unimodular. It's called. And then mathematician will tell you that there are 2 lattices. There are only 2 lattices. So candidate of gamma 16 is the root lattice of E8 cross E8, and the weight lattice of SO32. So these are the lattice which satisfy this condition. Okay. So thinking there, E8 is written here. In the lecture note, 7 lattice, right? 1, 2, 3, 4, 5, 6, 7, and 8. 8-dimensional. What is the thinking diagram of SO32 is something like this. So this kind of stuff. Let's see, 1, 2, 3, 4. So in total 16 again 16 node. So you have an 8 node for E8, and this is also 32. But since we have 2 copies of E8, you have in total you have 16 nodes. Okay. I mean, eventually, if you do the theoretical physics or mathematical physics, you have to learn this Cartan-killing theory for classification of semi-simple Lie algebra. I don't have time to do that. So, but so that you can just look at some textbooks. There are tons of them for Lie algebra and the algebra and its representation. Oh, it stops right here.
So you only considered about S transformation. So what's the constraint of the lattice coming from T transformation?
Good question. Oh, it has to. Good question. Somehow I missed a lecture note. Good question. So, yeah. You're right. For T transformation, you just shift tau bar plus 1, right? Tau bar plus 1. And it has to be invariant. So therefore, this means that from T transformation, PL squared has to be even. That's true. Thank you very much. So it has to be even. So therefore, this lattice is also even lattice. And plus, this will give you gamma 16 should be even. Thank you very much. Okay. And then look at the and then now, so we just look at the partition function here, and then one can read off what is the master state, how many master states, bosonic master states are there. Okay. So from bosonic mode, so left moving sector, this will give rise so this internal momenta, I takes the value for 1 to 16 for internal lattice, or for inside, this is torus coordinate, and this will give you the U1 to the 16, the massless gauge boson. So massless gauge boson. And then, if you look at the gamma 16, so this will give rise to the vectors, 480 vectors of length square is equal to 2. Length square is 2. That will also give you the master states. So if you do the PL, if the lattice is PL like a square, you get the +1, and you have a tachyon from bosonic mode, tachyon minus and the +1 cancel, you get the massless state. But there is a 480 vectors, such a vector, 0. So they're combined together. 496 massless gauge boson. And this is indeed will give rise to either SO32 E8 cross E8 adjoint representation. E8 adjoint representation, in other words, or gauge theory. So there's a huge enhancement at self-real lattice. So we see U1 is enhanced to SU2, as we saw in the S1 concatenation at the self-real lattice. In this case, U1 to the 16 and this the massless vectors in lattice will give you non-abelian gauge field, which is the huge enhancement from, U1 to some power to the SO32 to, or either SO32 or E8 equals E8. So that's what's going to happen in heterogeneous string. So, and then, so SO32, you already encountered type 1 theory. We already seen to get the tadpole cancellation, you need to insert the 32 D9 brain plus 1009 brain for type 1 theory, 09 minus. That will also give you the SO39. So heterotic 39 and the type 1, this is heterotic. And indeed, type 1 with SO32 gauge group is indeed S-reality. That's what we will see later. So the same gauge group is not coincidence. Oh, it's heavy rain. So it's not coincidence. So let's look at the spectrum of the massless spectrum of the heterotic string and take a break. So now I'm going to erase this part. Okay, let's look at the mass spec structure of a heterotic string. So G mu nu and the B field, and then phi, the zero zone. Again, it's easy to obtain. So you have the Navier-Schwarz vector, which is after GSO projection, this is becomes next massless. This is right moving or holomorphic. Okay. And then holomorphic sector, and then you have the alpha bar nu acts on the bosonic tachyonic state. So this it will give you the and the nu takes a value for 0 to 9. So you just avoid the internal torus part. Okay. It's nu. And then you have a supersymmetric, so Graffino, and then Graffino. You just have the Ramon sector. You have Ramon sector, and then you have the homomorphic sector. Sorry. You have the same thing, but you just change the next Ramon. And this is after GSO projection. And as I mentioned, there's the 496 gauge bosons. For either E8 plus E8 or SO32, which is psi mu. now takes internal value. So this I takes the internal value here. Okay? And that combined with the vector with level length is going to 2, that will give you 490. Yeah, I didn't write down. So I think I just plus and the same times PL squared. Maybe I should write down psi mu minus 1 half 0 and oops, sorry. And then it's super partner. So super partner is again, it's a supersymmetric series, so you have a same number of the Gaugini. So essentially S and the same thing. That's how I obtain the massless spectra of the hydraulic string. Okay. That's a super partner. You just change the holomorphic sector or moving sector to be the maybe short and S to the more. Okay, that's how I obtain the massless spectra. This is indeed is give you the D equal to 10, N equal to 1, supergravity with the super ML SO32 or EH plus E. The field for N equal to 1. N equal to 1 super ML in dimension. So supergravity, I will explain supergravity in later. But supergravity is low energy effective theory. Supergravity is low energy effective theory of string theory. Namely, low energy effective theory is you just look at that, go into low energy and just integrate all the massive moment. So you just only look at the massless moment. That's the low energy theory. So the supergravity is written in terms of all massless field of the string theory. You just ignore massive state. That's a supergravity. Okay, let's take a break. This is the bosonic construction of the hydraulic string, and then we will talk about the thermal construction of the hydraulic string later. Okay, let's take a break. Sorry, recently I'm so busy that even I don't have time to buy some sleepers on time. Okay, shall we start? Resume. So now we talk about the lattice compactation on the bosonic string, but there is another formulation of heterotic string. Which is the even though it's a bosonic string, there is a way to deform it in fermionic way, fermions. Since it is very nice lattice. So this gamma 16 is very nice lattice. This is so-called fermionic. So gamma 16 is the even self-dual and the unimodular, right? Self-dual lattice. So the bosonic fermions. Let's go fermionization. I mean, or boson fermion correspondence. Boson fermion correspondence in CFD, fermion correspondence in 2D CFD. This kind of phenomena are really common in 2D CFD. If you have this very nice lattice complication on S1 and so on, like for instance, I will give you the homework, next homework, how this fermionization occurs into the CFD in simplest setting, but this is very ubiquitous into the CFD. I mean, very common phenomenon. So we just consider a metal sector of the action as the 1/4 pi. 2/alpha prime. Stop writing. So this is the so this runs the bosonic coordinate mu runs for 0 to 9, but there is a from n. So this is homomorphic, but on the homomorphic part you have where a runs for some value. We will determine from now. From ghost, you have the usual superstring one. So for ghost, you have homomorphic anti-homomorphic sector, but for superpartner, beta gamma ghost has only homomorphic sector. So we just look at the homomorphic superstring, and then right moving is the anti-homomorphic is bosonic string, but it's described by fermion by lambda. So this lambda is the fermionization. Lambda bar. So remember that the BC, recall that the beta gamma is the superpartner of BC. So we just add only superpartner of the homomorphic sector, but not anti-homomorphic sector. Then let's compute the central charge. Cx, CBC of psi, CBC, C beta gamma plus C lambda. And what is Cx? What is Cx? It's what is the central charge of the boson? Single boson. 1. So it's 10 dimensions, it becomes 10. What is the central charge of fermion? 1/2. 1/2, but it's only holomorphic. Okay, psi appear holomorphic, only holomorphic. If you look at only holomorphic one, it's 1/4. So 1/4 times 10 is 5/2. And BC, what is the dimension of BC ghost? You have a pose. Huh? Holomorphic 13, but if you have also anti-homomorphic, you have a 26. What is a beta gamma ghost? How to get the so superstring to get the you get the right when d equals 10 it becomes 0. Okay, so 11 is coming from beta gamma ghost, but it's the only holomorphic contribution is 2, 11/2, and then C lambda, and then to the series. In order for 0 to be harmonic free, it has to be 0. So this is type 1 case. This is type 1 case. And d equal to 0. And then C lambda should be, in this case, 8. In order for the total central charge to be 0. Okay, so then the series is harmonic free. Then we know that under homomorphic contribution, under the fermion, under homomorphic fermion, each fermion has 1/4 contribution. To get the C lambda equal to 8, it should run from 1 to 32. Again, magical number 32 show up. Okay, so 32, 2 to the 5, which is 32, and so on. And now we need to impose the, in order for the theory to be consistent, we need to, again, so lambda has the boundary condition, either NS and Ramon. And the corresponding boundary condition, you need to impose the GSL projection in order for the spectrum is to be consistent. Here, NS and Ramon, so here, all A runs for 1 to 32, impose the same boundary condition. Okay, same boundary condition. All 1 to 32 is impose the same boundary condition, and we impose these. Eventually, if you impose the same boundary condition, eventually you get the SO32, as you can easily guess. If you, the later, we just shuffle the boundary condition for half of the fermion. The other half of the fermion, you impose other boundary condition. So you split A is 1 to 16, and then 17 to 32, and then you impose the different boundary condition for fermion. That will lead you to, as you can easily imagine, E8 cross E8. So let's first look at the SO32. So which I called HO. Okay, and also we need to impose level matching condition. Now it becomes n minus a. So this n bar minus a bar, like a superstring, type 2 superstring. And now a is normal order constant, which is the 8 over 24. Sorry, 8 bar. Yeah. And then 8 bar r, 8 over 24. Do you understand where did it come from? 8 over 24. Where does the 8 over 24 come from? This right moving sector, no. Left moving sector, anti-holomorphic. 8 over 24, where does it come from? Do you remember? 8 over 24? So just look at what kind of right moving sector we have. So right moving sector, we have the bosonic string, bosonic mode, okay, and also BC. So normal ordering really comes from the anti-homomorphic sector of the X, which runs from 0 to 9. D is equal to 10 dimension, and also BC goes to D equal to 10 dimension. That is equivalent to the taking light cone gauge, so that the 8 really comes from the dimensional letter group. 10 minus 2. Now 1 over 24 really comes from this zeta function regularization. Remember, zeta function regularization. That will give you 8 over 24. This is coming from the bosonic anti-homomorphic D equal to 10 sector. And then you have to do the normal ordering of fermions lambda. And then fermion lambda, so Navier-Schwarz, you have each fermion you have 48, as you might remember. And for Ramon, you have to have minus 24. Do you remember? So sum of n squared 1/2 is equal to 1 over 24, right? So that is bosonic 1 over 24. But for fermionic, you have a minus sign here. So that's how we get the Ramon. Minus 1 over 24. And maybe it shows this is equal to sum of, is it true? Yeah. This is coming from 1/2 of this, as you recall. Let me check. I think this should be the okay. Let me check now. It should be the case. So that's what we have learned in the superstring. Oh my goodness. I telling you completely wrong. There's no square, sorry. There's no square. There's no square. And then n is the, of course, positive integer. N is positive integer. Sorry. Good. There's no square. And that's normal on a constant. This is plus 1 and a minus 1. Okay. So left wing here is already computed by in type 2 or RMS string. Do you remember what is the A supposed to be? So this also depends on how you impose the boundary condition psi, right? And when psi is equal to ns and Ramon, A is equal to, as far as I remember, it should be 1/2. A is equal to 0. And this one half will give it tachyonic mode, but the GSL projection will remove this one. But R is equal to 0, so there's a 0 mode can act on vacuum. That will give you, and after GSL projection, you have an 8S or 8C. Do you remember? That's what's going to happen. So now we look at the first. If you look at the Raman sector, you have a -1. So therefore, if you plug into here, you have a +1, which is massive. So if you impose Raman boundary condition, everything the spectrum become massive. There's only. So let's look at the Navier-Schwarz, which is tachyonic, but again, GSL projection, you have to impose GSL projection, will project out tachyonic state. So here, Raman, everything massive, and from here, the vacuum is tachyon. And now, so we know that the right moving sector is not bosonic. Okay? So it's a bosonic string. So therefore, if you use the GSL projection for heterotic GSL projection, you get the bosonic is projected out, bosonic vacuum. And so therefore, after GSL projection, massless mode, left mover, RAI -1. Oh my goodness, I should. Sorry. I think I told you huge lie. Yes. I think I told you huge lie. Sorry. Okay, so sorry, I told you again. Sorry. So there's a contribution BC ghost. So contribution BC ghost, and then again you need to take into account this BC framework vacuum. So therefore, sorry. Okay, so the logic is as follows. So left movers, the vacuum is not projected out, okay, by GSL projection because it's fermionic. So 1 minus -1 is equal to 2. So 2 over 2 is equal to 1. So tachyon is not projected out by GSL projection. However, it does not match with level matching condition. Left mover is super string. So therefore, there's the only massless mode. Lowest at the ground state is a massless mode. Okay? So Raman equals to 0. And then Navier-Schwarz equal to 1/2, but that is projected out by GSL projection in right movers. Okay? So this one is projected out the right movers. So therefore, there is no corresponding object for tachyon in left hand side of level matching condition. So therefore, this tachyonic state, even though it's not projected out from the spectrum by GSO, it does not satisfy the level matching condition. Okay? So level matching. So therefore, it does not show up in the spectrum. So and at the end of the day, so we get the following spectrum. So so to preserve to be preserved, in order for the state to be preserved, you need to act as some bosonic states. If you act the Fermat states, they can Fermat states Navier-Schwarz vacuum is fermionic, and if you act one Fermat state, it becomes bosonic. Bosonic state will cancel 1 minus 1 is equal to 0. So therefore, it's projected out. So therefore, you have to act at least two fermionic mode in order for the states not to be preserved under GSO projection. And this is Navier-Schwarz, so therefore, the only master states is this one. And as you can see, this one is so alpha, so sorry, this is alpha. I runs for right home gauge. I runs for right home gauge, and this is just the homomorphic creation operator of -1 acts on Navier-Schwarz that will give 8 vector. And on the other hand, left mover or anti-homomorphic fermion, 2 of them can act on Navier-Schwarz. So since this is the fermions, A cannot be equal to B, but A is different B, that will give you adjoint representation SO8. So this will give you the vector boson. I think I made a huge, okay. Sorry, this should be bar. Yeah. And then, so this decomposition is SO8. That's Riedel group of, that is Riedel group of the space-time. And this adjoint is a little group of the I hope what I said is correct. Yeah, it's the typo. It should be bar here. Okay. Good. So this SO8 is a little group of spacetime, and this state is transformed as a vector, but SO32 arises from this Majorana spinner. So more precisely, these are Majorana waves. It's 32 dimensions, so it's okay to have the Majorana one. Okay, that's what's going to happen. So then, at the end of the day, so you just look at the spectrum of mass and state, left and right. One is the 8B and then 8C. After I just pick 8C for after GSO projection. 8B1, and then 1 and a joint. And again, so the joint is dimension is the joint is 32 times 31. It's a real and 498. Okay. This 498 show up like before, right? From bosonic construction. So this is 6. Okay, sorry. 6. Okay. So this is the dimension of the gauge bosons, and as you can easily see, it becomes one. It's a family of sync 28 plus 35, which is 5BG. So the dilaton, B field, and then graviton, and then its superparton will show up. So dilatino, gravitino, one copy. And now, so we have gauge bosons. And gravitino. Okay, so this is exactly what we have seen from bosonic construction. Well, of course, this mu, indices mu come from 8B, and indices AB come from here. So this guy coming from 0 and S alpha I minus 1. This is Ramond, whatever. So this is Ramond. So this is right moving sector, left moving sector is this. Good. This is exactly what we have seen from bosonic construction. Now let's move on to heterotic E8 plus E8. And now, so to get the E8 cross E8, we split the red mover fermions lambda bar A plus T plus T sigma 2 pi is equal to boundary condition. So we split in two groups, and then E has to be plus 1 minus 1. I already forgot which one is the correct condition. This is Ramond, and this is Levi-Strauss. So from here, so you have an S1 and S2, Ramond 1 and S2 to the full type of boundary condition, and let's look at the one by one. And due to these two splitting, the global symmetry is broken to SO16 plus SO16 instead of SO32. Previously it was SO32. And again, so we will look at the level matching condition. So and then just look at the normal ordering constant. What is NS and S? So we do the same thing for here. This is 1, but A bar Ramond 1 and S2 is equal to A bar, and S1 Ramond 2 is equal to, so 8 over 24 is the same, but now we have Ramond for half and NS for half from half, so we have the form, which is equal to C. So now we have masses, and how about A Ramond A bar Ramond is equal to -1. It's the same as before. And we impose the again GSO projection, which I erase now stupidly. So then again from here you have massive state, and from here again there is no states that satisfy level matching condition. Again 0 and S, no level matching. Sorry. 7. I choose the level matching is not satisfied. 4. So therefore, the taken from left mover is not present in the spectrum. So then, so again, it's a similar situation over there. You have, again, it's a typo here, minus I, 1/2, 0, and S1, and S2 is the 8B, 1. And then you have other one. Then you have 1 adjoint, 1, it splits. So now, maybe I should write down 1. And 1 adjoint. So here, the 3 indices are a little group of space-time, and then grow symmetry. So namely, so when you act the lambda A and lambda B, AB should be simultaneously, either AB should be simultaneously this one set of 1 to 16, or AB is simultaneously the sets inside this. You don't have the you don't have a mixed one. So therefore, so here are the joint. So dimension. So its dimension of the joint is so 16 is the here is the indeed equal to. The 20 dimension. But however, you have to be careful. There's another ground state given from the mixture of Raymond and S. Okay, so there is some ground state appear here, and you need to take into account this ground state. So, okay, I didn't explain properly that the reason why you should ask a question. The reason why it has to be the same is that the geosphere projection imposed independently. So the HE, so is NSI. You have to impose independently. So suppose if you take one of them is one of the A is in, so A is, how to say, one index is from here, B coming from here, then NS1 only it becomes the bosonic. So remember 0 and S is fermionic. If you only act on one fermionic, not fermionic, lambda. From correlation operator, it becomes bosonic. Okay, so therefore it's projected out from one of the GSO projection. The same thing. If you pick B from the out of 70 to 32, so then lambda bar B 1/2 minus 1/2 acts on here also become bosonic in terms of this GSO projection. So therefore, they have to take the simultaneously in the same set of the indices. That actually splits into the SO32 to SO16 to SO16. However, once we take into account, so we need to take into account this massless mode. So this massless mode is the 0, Raymond 1, and then NS 2, or 0, NS1, Raymond 2. Okay. From here, so again, so one of them are Raymond. So therefore, the 0 mode will show up. So A is either 1 to 16 in this case, and or in this case, A runs for 17 to 32. Okay. Then there is a 0 mode for fermions, Majorana fermion. That can act on the vacuum. That will create some states. And that will give you spinor states of spinor state of SO16 1 and SO16 2. I should call XT16 1 and 2. Okay? And then again, you do the similar exercise. So you do similar exercise, how to say, and then lambda k, 2k plus minus I, lambda bar, 2k plus 1. Yeah. And 0 mode, and 0 mode, and 0 mode. And then I just properly normalize 1/2. Where k runs for 1 to 8 for SO16 1, and k runs for 9 to 16 for SO16 2. And then this creation annihilation operator can act on the vacuum, so that at the end of the day, this will give you 2 to the 8, which is 2, 5, 6 states. Spinor rep of SO16I. And remember, you have to impose the GSL projection quadratic of Ramond I is 1 plus minus 1 to the F over 2. So therefore, you only pick the modular chirality. Okay? So again, so 2, 5, 6 is split into 1, 2, 8 S plus 1, 2, 8 C. And also, so therefore, GSL projection for Ramond, we pick one of them. Okay? So at the end of the day, so the spectrum looks like as follows. So 120 comes from the Fermat operator acts on the other NS, and then also you have 120 plus 128 come from Ramond NS plus, maybe I should write that like this way, 128. And then this will strongly suggest this SO 16.1 plus SO 16.2. But if you add them up, it becomes 1, 2, 2. So this is, you often do the following exercise. If you add them up, and this is indeed a dimension. Yeah, maybe when I say adjoint, I should write down SO. Okay. So therefore, this strongly suggests that if you combine two massive spectrum, SO8 is SO8, not SO8, SO16 is gets enhanced to E8. So that's a strong suggestion. And there are lots of, and of course, if you combine them together, you get a 4, 5, 6. You have how many of 4, 5, 6? Dimensional Arrangement representation of E8 plus E8. Okay. And then there are lots of evidence so telling that this E8 cross E8, again the Green-Schwarz mechanism. Again, I didn't write down the Green-Schwarz mechanism in lecture note. In a big breakthrough that if you consider D equal to 10 and equal to 1 supergravity, the gauge group has to be SO. Why SO 32 or E8 cross E8. And of course, there's some bunch of some exceptional other 4, 5, 6 dimensional gauge group will show up in at least supergravity, but the string theory, these two are only candidates. Yeah. Huh? Oh, why I can't keep making mistake? Sorry, I'm sorry. 496. Sorry. Yeah. 496 dimensional gauge group sharp in supergravity, and these two can be only in the superstring. Okay. And now we have some plenty of time. We know the mass spectrum of the string theory heterotic string. Okay. So heterotic string, I'm already super tired. So the spectrum is a bosonic spectrum phi and B mu nu and G mu nu, and a gauge field mu. This is a bosonic spectrum, and it's super bosonic. And as you can see, there's no Ramond field P form. So this means that from B, exists on B, this means that the F1 fundamental string exists and also NS5 string exists. Okay? NS5 exists from fundamental. So this fundamental string, electric couple, and magnetic NS5, magnetic couple B. However, no D brane. Okay. So this can be also seen from space-time viewpoint of d equal to 10. So the few strengths of, if you start at Cp plus 1, Cp plus 1, you just have the Hp plus 2, which is the extra derivative of p plus 1, Ramond flux. And this is the vertex operator, space-time vertex operator correspond to did in the homework gamma mu1 delta mu p plus 2 and psi r. Okay. However, we know that the right moving sector you have a Fermat because it's supersymmetric, but left moving sector there is no Fermat because it's bosonic in space-time viewpoint. So therefore, you cannot create. So there is no such a psi bar L. Well, left moving sector, you cannot have the psi L because it's left mover is a bosonic. So therefore, you cannot create the vertex operator corresponding to the Ramond few strings. So that's one way to see if there is no D brane in heterotic string. Yeah. Okay. And now, that's the story of we just covered 2A, 2B, type 1, and heterotic O, heterotic E, and here we see 11D Sugra. Okay, so now we just cover to here, and then we will go to supergravity. Okay. Any questions so far? Okay. So, superstring so we look at the massless state, ground state is massless, and square is equal to 0. And then next state is level n is proportional to alpha. So okay, let's so this is the n square alpha prime, and then there's a ground state and mass state, and 2. It's a level. There are a bunch of states. The massless state you have again like a phi, b, g, and so on, depending on string theory you consider. And you have excited states. In the homework, you just count how many excited states for type 2 theory. As far as I remember, 128 in holomorphic sector and so on. A bunch of states, many states, many massive states. Which is proportional to so therefore this and also you can create whatever ns on 0 ns and offer psi minus 1/2 and mu that will give you the ns the framework states so bosonic states, but you can act on whatever states, for instance 3/2, for sorry. For state to be preserved energy is a projection minus 3/2, so maybe 5/2 and so on. That will create a higher massive mode. So then the supergravity is just take the alpha prime to be very small. So alpha, as I mentioned, alpha prime is the only one coupling constant that is measured the string length or string tension or the massive state, the mass of them. If you take alpha prime goes to 0, so this state, so in other words, if you just get rid of alpha prime, this becomes 1 over alpha prime. 1 over alpha prime. Once you set alpha prime to 0, this mode goes to infinity. Okay, and you only look at the massless mode. Okay, and that is called low energy effective theory, which is called d equal to 10 supergravity. So what is the low energy effective theory? It's a weak electroweak theory. What is a low energy effective field theory? You guys should know. What is after Higgs? What is the low energy effective field theory of the electroweak theory? Something like that, as far as I remember. I don't know. The direction arrow should be different. Something like that. E plus. Let's be schematic. I don't know. Charge has to be conserved. So this is electroweak theory. Or maybe you can be quark. I mean, it can be quark. I mean, neutron and proton, it should be some 3 line here. If you take Lorenz effect theory, what is the theory? You don't know that? You should know. If you learn the quantum physics, it's called Fermi theory. In Fermi theory, you have the psi, I already forgot, gamma, mu. Essentially, the term contains something like this one. It is called quartic term by parameters. That will give you this kind of theory. But W boson is really massive, so you cannot see this W boson propagator. So this will become the vertex like this way. Okay? So this W boson is to become massive, so that if you go to low energy, you cannot see the propagator. So that this quartic term will give you this quartic interaction, and when the W boson is very massive. That is low energy effectivity. So, supersymmetries, supergravities, you just consider local supersymmetry. Okay, let's step by step. So local supersymmetry. I only have 10 minutes. So you just introduce P line or tetrad or whatever you call it. EA. I'm already super tired, unfortunately. Okay, and then you can just consider it just give you, oh sorry, this is the, yeah. So this EA M will give you ordinary coordinate to orthonormal. Okay. And then XM and the orthonormal. It's just coordinate transformation of orthonormal coordinate XA. So it just give you coordinate transformation by E. So in other words, G and N. I mean, you guys should know about this one if you work on the GR and so on. So here, eta is just Minkowski signature. It's just whatever, -1, 1, 1, 1. But whereas Mn is a non-trivial metric. So you can just get my metrics in terms of this eta and b. If you use the orthonormal coordinate, the crippled algebra is given by eta and b. Okay, so we are considered now supergravity is just you just consider how to say local Suzy, the gravity is becomes the coordinate transformation becomes dynamical, so that the it has superplanar. So in other words, if you start with gauge field, you have gauge E of supersonic transformation. On the other hand, you have, if you take EAM, so this tetrad or coordinate transformation also depends on now the position of x. Everything becomes local. Everything becomes local. And you just consider this transformation from just rigid metric to the dynamic metric, which depends on the coordinate x. Okay, is just a really rigid coordinate to the very dynamical. The metric is actually obtained by using this tetrad of phi. So you can consider this one encodes the gravitational dynamics. So if you take the supersymmetric variation of this tetrad, you should get the superpower. And this is called gravitini of spin 3/2. And this guy is called Gaugini because it's, what is the spin of Gaugini? What is the spin of Gaugini? Supersymmetry. So what is the spin of a gauge boson? Spin 1. Oh, this is spin 1. Spin 1. What is the spin of the graviton or graviton? You have 2 indices, you have a spin 2. And by supersymmetry, you do this one half. So the same thing happens for gauge field. Gauge in, it should have spin 1 half. So it's a parameter, but it has some space-time indices. That will give you spin 1, 3/2. And the M is covariant derivative of space-time. So this is covariant derivative of space-time. And then what we should. Sorry, I just got confused. Yeah. For gravity, it's a gravitino, and then we need to introduce. I just got confused. Okay, I understand what's going on. There's a lot of typo in the. I'm sorry, I think I made a mistake. Okay, so sorry, this is not true. This is not true. Sorry. This is true. Sorry. Yeah. So sorry, I made a mistake. So this is supersymmetric transformation. So and in lecture note I just call it psi n. Psi a, psi. I made a lot of mistakes. And then again I made a mistake. Yeah, this is correct. This is correct. Sorry. Lecture note. So this is gamma matrix coming from this Krifel algebra. And the epsilon bar is the supersymmetric transformation, infinitesimal supersymmetric parameter, and psi m is the gravity. So that's the, and then the action usually given by as follows: 1/2 copper square dx, and then square root g and r minus 2I psi m and p dn and psi p. Okay, so this is usual supergravity action. Yep. So this is the main idea of the supergravity. So you just consider the superpartner gravity and then just compute, construct the action which is coming from Einstein-Hilbert action, but it's supersymmetric invariant. And of course, so this is supergravity, and the super young males is again the same. Some coupling constant, G young males, and ddx as for G, and then you have F mu nu, and I don't remember the quotient, but essentially what you have is this lambda, the lambda bar, and the slash. And lambda. This is the supersymmetric action of super young males. Okay. So we have the gauge field and the gauge ini, and then you have a Dirac action. Supersymmetry requires it has to be massless. And a similar thing, you start with Einstein-Hilbert action, but you just introduce the gravitini so that it's invariant under this transformation. It's the same thing. Here, you just start with. Okay, I think I should write down trace. Wait, trace. Here, no trace. Sorry. Trace is coming from gauge indices, or maybe I can just write down the gauge index like this way. You have Yang-Mills action and the gauge in. You just have add the Dirac action for gauge in. And it becomes supersymmetric. And then we will consider how many supersymmetry you have left, and depending on dimension, the supergravity action will modify. That's what we are going to see in the next lecture. Okay, let's stop here. And homework is due on Sunday night, so that you have plenty of time to work out.